Morning, everybody. How was the weekend? It was a weekend? Yeah, just a weekend. Let's see, what's going on this week? No exam this week, right? It's next week? And then our lab this week is on moment of inertia. Okay, so I think we're still on track here. I did push back the chapter 10 homework. You probably all saw that, right? Made an announcement, changed the due date. You get like an announcement when I change the date, and then you got my announcement, right? That's how campus is supposed to work. And then you really want to kind of be ahead. You should be able to finish up chapter 10 homework after we're done today. I'm going to finish up chapter 10 and move on, start with chapter 11. 10 and 11, I mean, there's a lot of overlap there. You could probably already be doing stuff in chapter 11, especially the rolling motion problems. So make sure, when's chapter 10 homework due? It's like next Saturday, this coming Saturday, right? And then the chapter 11 homework is due that Wednesday because of the exam, right? So work ahead. Oh, I need to post this announcement too. I'm not going to be here on Friday. I'm going to Colorado to see my parents. So the GRASP will open at 8 a.m., not 7 a.m., and I won't be around. So just so you're aware. All right. Torque. We had started on torque, and I was complaining about hobbit holes and doors and all that kind of stuff. So let me drop on you something that's true, but I don't like it. First of all, before we get there, torque as a symbol, like how we write it down symbolically, it's the Greek letter tau, which technically is supposed to look something like that. It's like a, I don't know, like a curly, squiggly T, but typically gets written like in, if you're just writing it down on paper, you know, like a T would have the little piece sticking up above the crossbar, right? Okay. Tau gets rid of that piece above the crossbar, and it's one of the Greek letters. So again, we're using that theme where if it's in rotation, we're going Greek, right? Okay. Now, I'm going to give you the full vector definition of this later, after we've tackled something called the cross product. For right now, I want to talk about magnitudes of torque, and I'll show you how to deal with directions here in a little bit. This is how I like to teach it, think about it, and use it. And you may or may not see that written in a book or online somewhere. There's a kind of a special physics notation that's going in there. That upside down T that's between the R and the F, that means perpendicular to. So a torque is a distance and a force that are perpendicular to each other. Like we did last time, right? If you apply a force like directly at the axis of this wheel, the distance here would be from the center of the wheel to where I'm applying the force. But if there is no perpendicular component of this force, I can't make the wheel rotate, right? I have to come in and apply a perpendicular force somehow, some way, in order for any torque to take place. The same goes for when I open the door, right? Okay? I have to apply this perpendicular force to it. If I try to apply any kind of parallel to the distance from the axis of rotation, I'm not going to get any torque. And so I like to write it like this. And the reason I like to write it like this is because it gives flexibility. This can mean two different things. And we already have skills when it comes to finding components of forces, especially ones that are perpendicular to things. What do I mean by that? Let me draw like an overhead view of the door. So this is kind of like looking down on the door. There's the axis of rotation, or where the hinge might be. And if we come in with, like, say, a force, we either push or pull on the door, right on its outer portion right here. at some angle. And we'll measure the angle. We're going to measure it both ways. Let's measure the angle right here. Okay? First of all, to calculate the torque, what distance do I need? Radius, like what? From where to where? Good, right? We need to go from here all the way to there, right? This is my distance, okay? This is sometimes called the lever arm. And that's the R that goes into that equation right there. But I need a distance that is perpendicular to a force. Is that distance and that force perpendicular to each other? No. So what do? We find the components, right? Like we've done this before, right? F has got components. That one that points along the x, one that points along the y, and the one that we need, do we use sine or cosine for? How do you know? It's not touching that angle, and we're done, right? But, here's the big but. What if the angle we're given, is sitting in here? I better not call it alpha, let's call it phi. What if I'm given that angle instead? That is now f cosine of phi, isn't it? So whether you choose sine or cosine depends on where you are measuring this angle. What's the more important thing to remember about torque? What has to be true about the distance and the force? Perpendicular. If there's no perpendicular component, if I have a force that either acts like this or like this, how much torque is it going to apply? None, right? So that's why I like to draw it like this. Now, there's another way to find, and I'm going to introduce this to you now. You're going to be kind of confused, and it's okay. We'll come back to it in chapter 12. Let's say we have the same situation, okay, where here we have this force. There's another way to find a perpendicular distance and force. Now this method I like to call the line of action of the force, because that's what the engineers call it. If you just kind of draw like a dotted line that is along the line of action of this force, you can find the distance that is perpendicular to that line of action of force. Both of these pictures, okay, are going to give you exactly the same answer. If I have that theta, then this is theta, and that r right there, the distance that we need, maybe we'll call this, we'll call this distance d right here, okay? I have a triangle down there, and this side, this r, is equal to d sine theta. And so you'll end up with exactly that sine theta sort of same thing that we got up there for the purple one. Don't worry too much about this right now. I just wanted to introduce your brain to the other way of seeing a distance perpendicular to a force. This isn't going to affect us in chapters 10 and 11. It will affect us in chapter 12. So when we get to chapter 12, I'll kind of harken back to this and go, hey, you remember your brain? I'm trying to remind your brain about this line of action of the force. Now, the way you are going to see torque defined in the book, online, everywhere you go, is rather unfortunate. Because a lot of people, and this is true, it's true, will write torque as r times f times the sine of the angle between them. What we're really needing to do here with torque is do a cross product. We need to be able to multiply two vectors, a radius vector and a force vector, and get another vector out. Torque is a vector quantity. But we're kind of hiding that from you right now for good reasons. We'll get to it in chapter 11. But the reason I don't like that one is because you'll take it way too literally and assume you always have to use sine. But as I just demonstrated, whether you use sine or cosine depends on what? The angle that you are measuring or the angle that you are given, right? And so while mathematically speaking, the magnitude of a cross product is r times f times the sine of the angle between the two vectors, I would caution you against using or just believing that flat out. I would make sure that you understand that you're finding perpendicular things, right? And then let your tried and true... I don't know why it is that textbook authors throw away a whole skill set that we've been trying to teach you the entire semester about finding components of forces. They just have you ditch that for, just plug it in. And it's like, no, as long as we give them the correct angles, but the universe doesn't give us correct angles all the time. So I want to empower you to be able to do any situation and not be locked into thinking torque must always be calculated with a sine. Mathematically, it may be true if you're really careful about how you set things up. But in general, the one in the box is going to keep you safer and be used for every situation that you run into. All right, so as I alluded, torque is a vector, but you haven't seen any vector signs on any of the symbols that I put on the screen so far. For right now, we are going to use the directions, okay, of clockwise and counterclockwise to describe what's going on here, right? This is clockwise for you, okay, and counterclockwise. Those will be our two kind of vector directions for torque. They're a little bit of a lie, but they're a really useful lie for most situations. So we're going to have to determine which one's positive or negative, and that'll be our choice. But we're just going to use as our directions clockwise and counterclockwise, right? For now, okay? And we'll get to the rest of it later. Okay. The other thing about torque, what happens if I have something spinning and I apply torque with both my hand and the desk? So I've got a torque down here from the friction on the desk, and I got a torque from the friction in my hand. What do you think we can do with these two torques to find the net torque? Now this sounds an awful lot like, yeah, forces, doesn't it? And we had a way of dealing with this when it came to straight line things. And yes, it's back. Newton's second law. Coming for you. Liam.
Just for a question about like the vectors of a torque, is it like tangential to it, like this force, like this direction of being applied?
No. It's mutually perpendicular to both vectors. Did that mean anything? Yeah, a lot of vocabulary. Yeah, we'll get to that in chapter 11. I need to teach you about cross products first, and then it'll make more sense. For right now, we'll just go with what rotation does it cause? Clockwise or counterclockwise? Okay, so there's the linear version. Let's take a stab at what the angular version of Newton's second law might look like. So I've already let the cat out of the bag. Instead of adding up all the forces, we're going to add up all the torques. Okay? And then instead of A, what are we going to write down? Think Greek. Alpha, right? Angular acceleration instead of linear acceleration. We're going to write down angular acceleration. And then instead of mass, we're going to write down the table. What was the thing we used for rotational mass? That table that solved us from all the integrals? Moment of inertia. Excellent. Okay. So there it is. Newton's second law written down in its angular terms. So if I've got something spinning and I apply a torque to this, it will have alpha, because it has moment of inertia. Just like if I take a ball and I apply a force to it, because it has mass, I apply a force to it, it will accelerate, it will change its motion. In rotational terms, I can alter because it has moment of inertia, I can alter its rotation by applying a torque. So we're going to do the same things that we did before with Newton's second law, but we're going to do it for things that are spinning around in circles. So I've got an example here of how we apply all of what I just told you about, like R perpendicular to F and sum of torques and Newton's second law, all that kind of stuff. And we're going to do the example of a potter's wheel. I don't know if anybody's ever done this. It's kind of fun. It's like playing in the mud, but for adults. So I've got a little picture of it down there, right? But basically what's going on here, you've got this like potter's wheel, right? And it's got the lump of clay. And the way I sort of picture this happening is the potter, like turns off the motor and wants to stop the wheel from spinning. And so they take a rag and they just kind of press into the side until the wheel stops, okay? So what force, give it a label, give it a name, what force is applying the torque here? Yeah, it's friction, isn't it? Yeah. What kind of friction? Static or kinetic? It's kinetic. This thing is spinning. Here's like a top-down view for you, right? Rag comes in. Now, is there like a normal force here? Am I applying like a normal force to the wheel? Yeah, right? I've got two surfaces that are coming in contact with each other, right? But what direction is that force pointed? Toward, okay, let's just draw a circle. Let's see, here's our potter's wheel, okay? And then we come in with this, what do they say? It's 70 newtons. Okay, so there's the force, right? So we have a point here on the rim of the potter's wheel where we're applying this force. To be able to do anything with torque, we need distance and force perpendicular to each other. The distance would be the distance from the axis of rotation, from this case the center, to where the force is being applied. Are those two things perpendicular to each other? No, not at all. Is there a component of the 70 Newton force that is perpendicular to that distance? No, right? Okay. However, friction and normal forces are related to each other, aren't they? And so if this potter's wheel, let's just guess, right, that the potter's wheel is spinning around counterclockwise. And we apply this force, right? Which way will the kinetic friction be acting?
Perpendicularly downward.
It's perpendicular to the normal force. And how do you know it's down?
Because that's the opposite direction that we're going.
Yeah, right? The point on the wheel right here is moving upwards, isn't it? As this thing spins around, there's a bunch of like rotation, vectors, tangential V's, all like that, right? So this point where the force is applied, the wheel's moving that way. We know that kinetic friction always acts against the direction of motion. So that means, based on our diagram here, we have a kinetic frictional force that's acting downwards. Now, do we have a force perpendicular to our distance? Yeah, right? And away we go. Okay. Now, what else have they given me in this problem? They want us to find the coefficient of kinetic friction between the wheel and the rag. So, in general, I would like to start with energy if I could, but I'm not sure that I have all the information. I've also been given time, which is starting to make me really scared. Because that usually means kinematics, right? So as an example of a plan of attack and using Newton's second law, let's just get that down on paper and see where it can take us. Do we have a torque? Yeah. Yeah, the torque is coming from the friction. Do we have an alpha? Is the wheel like slowing down? Yeah, right? Okay. So the wheel's going around counterclockwise. That's clockwise for you. Counterclockwise, okay? And then comes in about 6 seconds later. Was there an alpha? Did the wheel change its angular speed? Yeah. Yes, okay? So if you had to guess which way alpha was pointed, clockwise or counterclockwise, what would you say? It's going to go, if omega, the angular speed, is going counterclockwise and it's slowing down, the acceleration, the alpha, has to be the other way. Okay, back when we solved Newton's second law problems, back in the dark days of chapters 5 and 6, we drew a free body diagram. We wrote down Newton's second law. We developed equations. And then we looked at our equations and decided what it was we wanted to solve for. Do we have a free body diagram of sorts? We do, right? We've got objects, we've got forces, we've got labeled forces, right? One of the key things about a free body diagram is defining what we call positive. And there was a rule that I taught you about, a rule that I always obeyed, it keeps me safe, about the direction you want to call positive and the acceleration. You remember what the rule was? Not the thumb. Well, it was a rule of thumb, right? Meaning it's an old-fashioned phrase for always do this. Make positive the direction of the acceleration. We have two directions in this problem. And those directions are clockwise and counterclockwise. The only real two directions we have for torque. So which way, clockwise or counterclockwise, do I want to make positive? Why did you say clockwise? Because that's alpha, right? In the way we've set up the problem, the way we pictured it in our head, right? We're saying top-down view, this thing is rotating counterclockwise. Because it's slowing down, alpha must be clockwise. And so we'll call, and what I usually like to do is I like to kind of draw a curvy arrow and put a positive sign in the middle. That tells me the direction that I'm calling positive, right? This thing, the curvy arrows wrapping around, this is kind of a Mr. Baloghism. Sometimes I'll even write down either CW or CCW to remind myself of kind of what I've picked. This is exactly the same idea as picking like positive X and positive Y on a slope, okay? You want to nail down what you're calling positive. It's going to keep you safe when we start getting into all of these directions, okay? The good news about Newton's second law in rotational terms is it's one-dimensional. When we did it in linear terms, we got both x and y components of things. And we ended up with like 4 equations with 4 unknowns or 6 equations with 6, whatever was going on, right? And it was bad. This rotational equation is one-dimensional in the sense that it only has 2 directions. Positive or negative, clockwise or counterclockwise. It's not like there's another axis or direction we can go in. So that's kind of nice. Okay. So we can find some torques. We'll do that in a bit. Alpha. Do I know anything about the acceleration? Unfortunately, I kind of do. They don't tell me straight out, do they? But can we find it? Do I need kinematics? Why? How do I know I need kinematics? Time, right? They gave me the time. Liam.
What unit is the coefficient of friction in?
It doesn't have any units.
Does it have any units?
It's unitless. Because mu is equal to the frictional force divided by the normal force. Those are both measured in newtons.
Yep.
Newton divided by Newton is no unit. Yeah. The other thing I just realized I forgot, thank you, is the units of torque. What are the units of a distance? Meters. What are the units of a force? Newtons. So the units here appear to be a Newton times a meter, which we've run into before. A force times a distance is work. It's also a Newton times a meter. We don't give torque a different unit name. Torque is measured in Newton times meters, or Newton meter. Work is measured in joules, which happens to be equivalent to a Newton meter. I know this is confusing and I can't fix it for you, okay? But they are not the same thing. Work is all about energy. Torque is all about getting things to rotate, changing their energies. But yeah, we just call it Newton meter. In the stupid unit system, that would be foot-pounds. Pounds, feet, whatever. All right. So back to this. I can find my alpha. I'm looking at this going, I'm going to need my alpha, I'm going to need my moment of inertia, and I'm going to need my torques. I'm putting the torques off for a second to do something I already know I know how to do. I can use the first kinematic equation to solve for my alpha. And I think I've been given all this stuff, right? Oh, shoot.
You gotta convert that.
Can this problem get any worse? Do I even have this one written down? Yeah, I do. 50 revolutions per minute, that right there, okay, is equivalent to 5.24 radians per second. I'm going to save time by not showing you how to do that, because I've showed you how to do that a lot, okay? So I do 5.24 minus, oh no, the other way around. It stops, its final velocity is 0, its initial is 5.24 radians per second, and then I divide by 6 to get myself negative 0.873 radians per second squared. Now, what's the negative sign doing there?
It means it's going the opposite direction.
Not direction. What does the negative sign in kinematics usually mean? Slowing down, right? It's slowing down at 0.873 radians per second squared. Okay, so I got my alpha. Moment of inertia. Well, is it mass times radius squared? So the potter's wheel, right? Solid, flat, stone, or synthetic disc. Yeah, it's going to be this one, isn't it? It's going to be that right there, 1/2 mr squared. So my moment of inertia in this problem, 1/2 mr squared. They give me the mass, 100 kilograms, and they give me the radius, 1/2 meter. That was nice of them. And that moment of inertia turns out to be 12.5 kilogram meters per second. No, kilogram meters squared. That's it. Okay. So I got my alpha, I got my I. So let's get that down. Notice I've dropped the vector signs off of this now because I just need magnitudes. And I have my one torque. Well, it's R times F, perpendicular to each other. Right? And I know the distance. The force is going to be the force of friction. And that's going to be mu times, run, everybody run! And now I think I've got everything, don't I? Do I know my moment of inertia? Yeah. Do I know my alpha? Sure do. Do I know my R? Yep. Do I know my N? Mm-hmm. So I can solve this for mu. That's going to be I alpha over R times N will be my coefficient. Plugging and chugging, 12.5 over 0.873 divided by R times, R was 0.5 and 70. You notice I dropped the minus sign on that alpha? If I left it in there, I would have gotten a negative coefficient, but can coefficients be negative? No. I just need the magnitude of alpha at this point. I know the direction of the torque. I know all that stuff. Okay, so I put all that in my calculator, and I got 0.312. Yeah, you got that too? Yeah. Excellent. This is probably too much for Monday morning, which I think could be said about all of physics. What didn't we talk about this morning so far? We did kinematics, right, which we studied last week. We got this new idea of torque. The table was involved for moments of inertia. What are you being asked to do right now? Everything, right? Everything is coming back. The new stuff that we've learned, old stuff from previous chapters, right? It can be a lot, but as you give it time and you really work at it, it'll start coming in. Again, just to kind of overview this one, we use Newton's second law because it was asking about a coefficient. That's usually Newton's second law. Sometimes you can get away with energy, but in this case we had to use Newton's second law. We had to use kinematics because they gave us time. And then looking at this, I was like, okay, I need to have my moment of inertia, I need to have my alpha, and I need to have my torque. And so I went looking for all of those different pieces. My moment of inertia came from the table. My alpha came from kinematics. And then this torque part I just put together, remembering how fun things were in chapters 5 and 6. It really is a coming together of a lot of different things that we've done so far. I don't think so. It's just a mass times a distance squared. That's not a V, it's an R. No matter how hard I try, it's not your fault, it's mine. R squared. There we go. Yeah, 1/2 mv squared would have been kinetic energy, right? That's so much better. Let's just do that instead. Why didn't you drop the negative? Because I didn't. So the negative sign right here just means it's slowing down. I set direction to be positive in the same way that the acceleration was going, which lines up with the torque direction that I had. So my alpha and my torques were both positive in that. I could have made them both negative if I wanted to, and then the negatives would have canceled. So just because I get a negative sign out of, say, kinematics, that doesn't mean I just plug that negative sign into my Newton's second law equation. The direction of things in Newton's second law depends on what we draw in our free body diagram. Good question. One that I often forget is a question. Okay. Boy, this just pulls up all kinds of PTSD, doesn't it? It is. Let's, we're going to do, there's going to be friction in this problem. The friction is going to be on the surface, not in the pulley. Okay? So, back when we did this in chapter 5, first did this in chapter 5, we conveniently ignored the pulley. We said it was a massless, frictionless pulley. And the reason we made it massless and the reason we made it frictionless is to make it easy. Because if we don't make it massless, What does the pulley have? It has moment of inertia. And because it has moment of inertia, it's now something that we have to keep track of in our Newton's second law analysis. We know this is Newton's second law because it's an inclined plane with connected objects. There's going to be forces, right? And so let's tackle this and see what happens when the pulley now has mass. We're going to need to remember stuff from chapter 5, but I think we can handle it. The approach is draw free body diagrams for all of the objects in the problem. There are more than 2 objects now. There's mass 1, there's mass 2, and there is the pulley. You can see I've already started sort of a zoomed in version of the pulley. We'll get to that in a second. Let's just do the chapter 5 stuff. Let's do mass number 1. We need to identify all the forces that are acting on mass number 1. Can you give me a force and like the force's name and the object that's causing it? Tension. So let's get actual, there we go. Tension acting up, right? And it's being caused by the string. Okay. Normal force being caused by the surface. Got gravity, right? Earth's causing that one. None of these are surprising, right? This is all what we had before. I did tell you there's friction between the surface and the block. And I'm just going to tell you it's kinetic friction. This block is sliding up the slope. All right. Do we have any other things, objects that are pushing or pulling on this block that we haven't taken into account? Thank goodness there's no springs, right? Okay. What about block number 2? Does it have weight? Yep. Does it have tension? Yep. These free body diagrams aren't finished. What's missing? Yeah, which way is positive, coordinate systems, all that kind of stuff. So since it's sliding up the slope, we don't know if the acceleration is 0, positive, negative. Let's just pick one. Shall we say that the acceleration is positive up the slope and down over here? Seems fine. Okay, so that means that positive x will be up the slope. I'll make positive y perpendicular to that. So what's the positive direction I want to give for mass 2? Just to keep things consistent. Down. Follow the acceleration. So this will be plus y. All right. So everything on the screen right now is not different from chapter 6. Chapter 6 where we did connected objects with friction. Here's where it changes. Because the pulley has mass, the tensions in those strings are not the same anymore. The tension up here and the tension down there are going to be different. Yes, Lauren, it is as bad as you think it's going to be. Lauren just put her head in her hands, knowing full well that we just introduced an extra unknown into the problem, okay? All right, so a pulley having mass changes the tensions. The reason it changes the tensions is because now the string not only communicates the force of like the tug of war between the masses, it also has to fight with or against the moment of inertia of the pulley itself. And so the tensions cannot be guaranteed to be the same on either side. It all depends on what the pulley is doing. So what I need to do now, and here's kind of really the new part for torques and rotational forces, all that kind of stuff, is I need to apply Newton's second law to the pulley now. So in this top diagram, you know what? we'll get to the pulley in a second. Let's do this. Let's do Newton's law in linear terms first. The entire free body diagram I have written in red, okay, is chapter 6, with the sole change of the tensions not being the same. Okay, so for mass number 1 in the x direction, m1a equals, well, I didn't go and find components, did I? That one right there, that's m1g cosine theta. We know all this already. This is m1g sine theta. Been here, done that. Okay, so let's see here. In the x direction, I've got T1 minus the friction minus m1g sine theta. I think I did that right. And in the y direction, I've got 0 equals n minus m1g cosine theta. Again, you could go back into your chapter 6 notes and see exactly that thing. The x direction, there's nothing going on. And in the y direction, m2a, what have I got? I've got m2g minus t2. There we go. Okay, so there's Newton's second law coming straight out of chapter 6. In fact, I don't think any of those equations are any different with the exception of that right there. T1 instead of T and T2 instead of T. And they are not the same thing anymore. Okay, so now we come down to the pulley. And a free body diagram of the pulley, a free body diagram in rotational terms. Okay? We are applying Newton's second law. I alpha equals sum of the torques. And so this means we need to find torques, we need to find moments of inertia, we need to find alpha, we need to do a bunch of stuff. So first things first, same thing we did up here. Ask ourselves, what forces are being applied to the pulley? So what objects are pushing or pulling on the pulley? The strings, right? Strings on both sides. This upper string, this one right here, which way is the tension acting? Remembering the tensions can only pull. They cannot push. Well, it is perpendicular automatically because it's a round pulley. But is the tension acting up that way or down that way? Down? This way? Which way is the pulley accelerating? Clockwise or counterclockwise? Clockwise. How do you know it's clockwise? We kind of said that, didn't we? We said acceleration was up the slope. We said acceleration was down for mass 2. And so that means we want to set the alpha, the positive direction, to be clockwise in order for these things to all be consistent. Can a tension acting up here push on the pulley? What happens when tensions try to push? It just goes slack, doesn't it? Tensions can only pull. And so because mass number 1 is being tugged up the slope, the pulley is being tugged down the slope. There's a Newton's third law interaction. Same force, equal and opposite directions, right? If the pulley is pulling up on block number 1, block number 1 pulls down on the pulley. Okay, using exactly the same ideas and arguments, what direction does the tension 2 act, up or down? It's got to act down. It can't push up, right? It's acting up on mass number 2, which means it has to be pulling down on the pulley. And you can kind of draw those in if you need help. Okay, you can draw those in up here. Okay, just to show that like that tension's pulling on either end of that string, even though it's one continuous string going over the pulley, but where it hits the pulley is like a point where it's pulling on the pulley. those have to be equal and opposite. And just to be clear, these are Newton's third law pairs because it's the same force in two different objects. These two are not Newton's third law pairs. Why are they not Newton's third law pairs? How many objects are we talking about when we do T2 and M2G? Just one object. Those are forces acting on M2. But look at these two T. Look at these two T2s. How many objects are they acting on? It's one force acting on two objects, right? That's Newton's third law. Whoa! Okay. Torques. Torques need perpendicular distances, don't they? Well, lucky for us, if it's a circular pulley, then you're guaranteed to have a perpendicular distance to the force. Whatever angle that string comes off of the pulley, okay, it's always going to be perpendicular because the string comes off tangential. That's not true for elliptical pulleys. There are some pulleys that have a cross-section that's an ellipse, not a circle. And you get some really cool mechanical advantage out of the changing radius of an elliptical pulley to affect different things in a system. But we're not going to do elliptical pulleys in here. We're only going to do round ones. And so if you see a round disc, a pulley, something, and you've got a string that's coming off of it, it doesn't matter. Like you can have like a pulley and strings coming off like this, or a pulley with strings coming off like this. These are always going to be perpendicular no matter what. That's just kind of the nice thing about circular pulleys. Okay, so now that I've got my forces and I've checked to make sure my distances are perpendicular to my forces and I've defined a positive direction, I can now write down the Newton's second law torque equation. Just like up here where I start with MA equals and then I write out all my forces, I'm going to do the same thing. MA instead is now I alpha. I just write I alpha equals, it's like a template. It's like it's going to be that same thing every single time, okay? I'm not going to think about that because I don't have to. I've gone and made sure that my directions are going to be consistent everywhere in my problem, okay? So I can just write down I alpha equals, and now I'm going to do a three-step process, just like this is the training wheels on here, right? And I strongly suggest you follow these steps when you're thinking about torques. Torques is a new thing for you, so you want to break this down. Eventually you'll get to the point where you can combine maybe a couple of these steps. But the first thing you want to do is ask yourself, how many torques are acting on the pulley? Two. Write them down. Like just what I mean by write them down is just write torque 1, maybe torque from T1, and then torque from T2. I'm just getting down the fact that there are two torques. If there were 3 strings or whatever, right, I would write down 3 terms, or maybe there's only 1 string or whatever, right? In this problem, I've got 2 tensions. They're both applying the torque, so I'm just going to get down the fact that they are torques. Second step is now go and look at the directions of the torque and assign a positive or negative. You'll notice this is the same sort of steps that we learned back in chapters 5 and 6. Remember I said write down the forces and leave a space and then go back and do the directions? You want to break it up and think about all of these things until your brain gets used to checking directions and all that kind of stuff. So, how do we determine the directions of these torques? Look at how, in isolation, the force wants to turn the pulley. Let's take a look at tension 1. If we ignore tension 2, we pretend it doesn't exist, what kind of torque, positive or negative, would tension 1 apply? Negative. Tension 1 wants to get this whole thing to rotate, in the counterclockwise direction. It's kind of tugging on it. If you need to, like, grab a dinner plate or something, right? Okay, and like, it's coming along and it's pulling along up here, right? Which way is the wheel rotating? Rotating counterclockwise, isn't it? Okay. What about tension 2? Which way is it now rotating? Clockwise. So the fact that T1 makes it go counterclockwise means we're going to give it what sign? Negative, because we said clockwise was positive. So if T1 is causing an opposite, then we're going to make T1 be a negative torque. We already established that the torque from T2 is going to be a positive torque. Third step. We've identified how many torques we have. We haven't written them down really symbolically at all, just sort of some labels. We went and checked the directions. And we made sure we got our positive, negative straight. Third thing we're going to do now is we're going to actually write down what the torques are. Mathematically, what do they equal out to? By that I mean all torques are distances perpendicular to forces. We already know it's perpendicular. We always know R and T's are all perpendicular to each other. So now I can come in here and write down, the negative sign just comes down from the line above. T1, the torque from T1. Well, what's the distance to T1? R. And what's the force? It's T1. So there's the torque. Plus, what's the distance to T2? Also R. And what's the force? T2. Trying to get from here directly to here while holding it all in your head is dangerous. I really implore you, like, write down just a torque symbol, just get down how many torques you have, then give them their proper directions based on your picture, and then write down their mathematical definition. That's going to help you not make as many mistakes along the way. Eventually, will you get to the point where you can probably just write the torque and then go back and do the directions? Probably, yeah. Right? But at first, you really want to make sure your brain is learning these steps. All right. We can solve for just about anything now. Really. We've got, I mean, I know there's no, like, I didn't specify a problem. Back when we did these back in chapters 5 and 6 and stuff, we could have solved for the coefficient of friction. We can solve for the acceleration of the system, which is what I'm going to do now. I'm going to solve for the acceleration of this system. So what I'm going after here, there's an acceleration there, there's an acceleration there. Is there another place that there's an acceleration? I said the tensions were different. Are the accelerations all the same? How do you know the accelerations are the same? They're all connected to each other by physics string. And physics string doesn't stretch or break, right? It keeps things connected. So as long as all these accelerations, as long as the string is not changing its length, which we won't do to you, we know that those accelerations have to be the same. All right. Looking ahead and solving for acceleration, I have a lot of unknown things. I don't know what T1 and T2 are. So we're going to have to get rid of those. Do I know what F is? The frictional force here? We're solving for acceleration. I want these accelerations. I assume that I know my masses. Right? Usually we know the masses and the angles, right? So known, we usually know mass and angles, and we know what planet we're on. Let's say that we also know what our coefficient is. So how do I deal with this F? How have I always dealt with friction? Fine. All right, so I got that. All right, so let's see where this takes us. The fun goes in here, but the normal force goes in there, doesn't it? That's not any different than what we've done before. So this is m1a equals t1 minus mu m1g cosine theta minus m1g sine theta. I'm just doing this fast because I've done it before. And then over here, nothing is, I mean, it's just m2g minus m2a. I'll rearrange this one for T1. T1 is going to be m1a plus mu m1g cosine theta plus m1g sine theta. Okay? So I found T1 and T2. I cannot set those equal to each other, right? I can't just solve for acceleration because I'm going to end, I still have two equations with two unknowns. Let's drop down and use our blue equation here. I mean, could I, and I will, okay, but now that I know T1, can I stick it in here? Yeah. And now that I know T2, can I stick it in there? Yeah. But before I do that, before I get that mess on my hands, right, I've got to deal with my I alpha. What is that the moment of inertia of? It's the pulley, isn't it? So how do I find the moment of inertia of a pulley? Not mr squared.
Isn't it like a thin?
Probably this. Almost every pulley is going to be like a disc. It's not going to be hollow air, right? There's got to be spokes and things in it. So we'll use the solid cylinder for this one. What? No. I moved this term over, and it became positive. I moved this term over, and it became positive, and this was still positive. And then I just reversed the order that I wrote things in. I know that confuses a lot of people when I do that, but it's still math. All right, so we're going to use in blue. 1/2 mr. So what m is this? It's the moment of inertia of the pulley, so it's the mass of the pulley, which hopefully we have been given. Whee! All right, and then the r squared equals RT2 minus RT1. Cleaning this up just a, oh, I forgot my alpha. Can I get rid of one of these r's? Yeah, got that in every term. Alpha.
Acceleration of tangent over r.
So tangential accelerations is equal to r alpha. What I have is a tangential acceleration. So a is equal to r alpha. So that means alpha is equal to a over r. And there goes my last r. R a over r. So the r's cancel, equals T2 minus T1. So what have I got here? I've got 1/2 the mass of the pulley times the acceleration equals T2 minus T1. And so really, I should put T1 into there, T2 into there, do a whole lot of math, and get the following symbolically. Needed more room. G, quantity, m2 minus mu m1 cosine theta minus m1 sine theta all over m1 plus m2 plus the mass of the pulley over 2. Let me add a page. Thank you. I know, it'll come back. Don't worry. Just don't worry. That one. I just want to shortcut this. There you go. There's the work. Okay, it'll be in the PDF. I know it's hard to see on the screen, right? But the gray part where I said a miracle occurs, there it is. Okay, if you want to see all the algebra that gets you there, right? Okay. Like I said, a lot to throw at somebody on a Monday morning, right? What on the screen, what color on the screen is the new stuff? Blue. Focus on like that, right? The red stuff we've done before. Now that doesn't mean you remember it. It doesn't mean that you understood it then or now or anything like that, right? But it is something that you've got in your notes. You can go back and, like if I went too fast on the red part today, you can go back and I spend more time on the red part back in chapter 6, right? The blue part is new and there's new skills in there just to break down your new skills, right? Torque, what it is. How to write it out and apply it in Newton's second law. A new kind of free body diagram that isn't so much about X and Y as it is about clockwise and counterclockwise. And you're going to get practice in your homework applying these rules. You're going to have to draw a free body diagram, think about what's positive, write down what those torques are. Make those mistakes, try to make them as fast as possible with each other to just get the mistakes out of your system, and because you're new at writing down torques and things like that, and you'll get there. Honestly, how long would it take you to do a problem like this on the exam? Like the whole 2 hours, wouldn't it? Easy, right? So am I going to dump something like this complete on you on the exam? Of course not. Now, will I expect you to know how to identify a torque and its direction and write down Newton's second law and all? Yes. But what could I do to make this mathematically much easier to do on an exam but still test you on the blue part? I could actually give you like T1. I could say tension 1 is this. And all of a sudden, boom, you don't have as many unknowns to deal with, right? So that's one easy way to do it. I could also just grade you on the setup, right? Give me the red and blue parts, okay? And I did that on the last exam for you, didn't I? Like those of you that set it up correctly but got it wrong subsequent in the math, I was like, fine, you got it set up right. You know the physics, okay? So there's different ways for me to do that. It could become a conceptual question. It could be, here's the problem. Which of the following torque equations is correct, right? Give you the correct one and then maybe flip signs or do something weird with the others, right? And so it's forcing you to go and apply the physical principles. So I'm not going to give you a 45, 50-minute problem to do on the exam, right? I'm going to find ways to figure out what you know. And so you want to tailor your studying towards knowing what I'm asking you to do. You guys now know I focus on setup. I focus on what do you know conceptually, right? And I'm a little bit more lenient when it comes to actually pulling the math off. Your bosses and your engineering professors won't be as lenient. You'll get there. You'll get there. All right. We'll set this one up. We may not get to the end. Okay. But again, just getting us some familiarity with applying Newton's second law in its rotational format, right? In its rotational form. Whatever's going on here, we know that this is going to be an example of Newton's second law in rotational terms. Now, it may not be the only one we need. We'll probably also need to use this because I've got that hanging mass down there. But I know that there's rotation involved here. This is going to happen. This looks a little bit like one of those old-fashioned wells, where they've got the crank where the bucket's on the end of the rope, right? And the bucket drops down and you pull the bucket back up as you turn the windlass. But we got this object attached to it, right? And the string is wrapped around. It could be like a fishing reel too, right? Like this is your hook and bait and things right here. And that's the reel where the string's wound up on the wheel. Inner radius, oh my gosh. Okay, what the heck? It's wrapped around, oh, so I see. It's got a radius, it's like it's got a big radius to the outer part of like where the string is being wrapped around, but then there's like an axle, something that's got like a smaller radius in there, maybe where there's, oh, there is friction. So in this central axle area, I'm going to take the blue, oops, I'm going to take the blue off, okay? That central area right here, okay, which is the axle, there's friction as this reel part right here goes around. Now, which way is this hanging mass accelerating? M1. Probably down, right? It's free, it's just hanging down. So I'm going to assume that the motion and the acceleration are both down, which means for positive alpha, I have to pick which direction, clockwise or counterclockwise? I better pick counterclockwise for my positive direction and my alpha. Okay, so I've got that, how do I know? Okay, I need to be able to write down Newton's second law. So I need torques and like distances and forces perpendicular, right? Okay, you know what? Let's do what we know first, chapter 5 and 6. Mass number 1. Does gravity pull down on it? Yeah, does tension pull up on it? Sure. This is going to be M1A equals M1G minus T. Do I hear any complaints there? We've gotten that so many times, right? I'm calling down positive because the acceleration is positive. Okay. To be able to do the torque, though, I need to be able to find a distance perpendicular to a force. What's the force? What force is acting right at the point of contact there? It's tension, isn't it? Acting downwards. Ooh, where's the friction acting? Yeah, on the inside axle, right? So they don't tell me where. Like it could be here, 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 here, probably everywhere, right? But we can pick just one spot on that inner axle and have it be representative of all spots. Because, let's see, if I pick here and the whole reel is kind of going around this way, right? What direction would the friction, the kinetic friction, be acting? Right or left? This would be against the direction it's going, right? But what if I picked this spot? It would be down. What if I picked the top? All of these pictures have exactly the same direction of torque and magnitude of torque, because the R is the same and the F is the same. So it doesn't really matter where I pick it. I just need to pick it. So I'm going to pick down here, okay? So my friction's going to act there, and it's going to act with a distance R. Okay. So what have I got? I've got I alpha. We'll deal with that in a second. How many torques are acting on this whole thing? 2 torques. What are they? The friction torque and the tension torque. I'm just writing tau sub and then my force symbol. What's the next step that I do? Direction. Okay. Friction, it's kinetic friction. What do you know about it? Opposite the direction, right? So put a minus sign on it. And the tension? It's causing it to rotate counterclockwise, so those will be positive. Okay. Real of outer radius are inner radius. Okay. Ooh, they're giving me some information in the problem that's going to help me with my moment of inertia. It's got an outer radius and an inner radius. Yeah, probably this one, right? So this is going to be 1/2 m2, because they said that the cylinder has an m2. And then it's going to be r squared plus little r squared. Yep, r1 squared plus r2 squared. Okay. Equals, and then now I need to write out what my torques are. So the negative sign comes down from the line above. And what's the distance to my friction? Remember, torque is r perpendicular to F. So the distance is little r. The force is my force of friction. Plus, and now what's the distance to the torque? Big R. Times torque. Find the acceleration of, I missed an alpha somewhere. There we go, alpha. All right. Over here, I've got Newton's second law down there in red. There isn't much I can do with any, but I can do my trick where alpha is equal to A over R. And then I can substitute this tension into here. We know F, it's just a number, so we don't need to worry about that. Yeah, I think away we go. 1/2 m2 big R plus little r squareds. A over little r equals negative little r times F plus r times this mess. That's going to be m1g minus m1a. Because I did not do algebra over here. And then that gets solved for the acceleration, which I kind of wrote down. You do a bunch of algebra. I'm out of time to finish that one up, and I'm not going to finish it, but I've showed you in here how to deal with, again, two differing torques, right? In this last problem, we had the same radius on those two torques, but here we had an object where we had forces acting at one position on the object, and then a different set of torques acting at a different position on the object. Well, yeah, you can see it on the PDF, but.
Also for the one with the real?
Oh, no, I don't have it in my notes. Yeah. Solve that for A. You get 2 terms. I think it's safe to say that might be the hardest day of this semester. Just because there's so much in this. So go home, unpack it, repack it, package it up in a way that you can do it, and you'll be all right. We'll start chapter 11. Is that the right number? Chapter 11 on Wednesday. Have a great rest of the day.